Hello everyone. Welcome to the day 15 of the machine learning teach by doing project. In this day, we have three agendas. The first thing which we are going to look at is this idea of solving machine learning problems using optimization. The second thing which we are going to look at is introduction to the concept of logistic regression. And the third thing which we are going to look at is the sigmoid function, what it really means, and why it is so important for logistic regression. In fact, in many modern ML algorithms, sigmoid function is routinely deployed. So, this particular lecture will also serve as a very nice visual introduction to what the sigmoid function really represents. So, let's start with the first aspect, which is solving ML using optimization. So, if you think of the perceptron algorithm, or even the random linear classifier algorithm, someone needed to think of these algorithms. So they came from our intuition. Uh, but what if we want to solve complex ML problems? So every time we want to construct new algorithms, we cannot rely on human intuition, right? What we need is a machinery. What we need is a machinery that will derive uh, or that will come up with ML algorithms for any problem. So we need a machinery or a methodology which will help us derive an ML algorithm for any problem. Perceptron, of course, was a genius idea. It was a brilliant way of updating the theta and theta naught. But what if we cannot come up with such algorithms each time? We need to devise techniques or methodologies which can help us to find ML algorithms for any given problem. And that's the reason why machine learning practitioners uh, turned ML problems into an optimization problem. So optimization is a field, is a mathematical field which has basically advanced very rapidly, and there are so many techniques which we already have in the domain of optimization. So if we can think of an ML problem as an optimization problem, we can use all of those techniques to basically solve an ML problem. What is meant by optimization problem? Essentially, let us look at the next part, which is ML as optimization. So optimization essentially means there is a function which you want to optimize. So for example, if I want to book an Uber, the way the Uber algorithm works is that based on my location, based on which drivers are close to me, based on the ratings of those drivers, based on my willingness to pay, Uber will assign me the best possible driver. That is an optimization problem. And the function here, which Uber is trying to optimize for, is assigning me the best driver. So, optimization problems we encounter every day in our day to day lives. When we want to go from place A to place B, we probably want to choose the travel route which leads to minimum possible time, right? That is an optimization problem. We are optimizing for time here. So, essentially, in any kind of optimization problem, there is a function which is called J, which we need to optimize. And that J depends on theta, which are parameters. So, in terms of ML, this j will be the loss function which we want to minimize, and theta are the parameters. So such as if you think of or rather those j is not exactly the loss function. I'll come back to it. For now, let us call j as the objective function. So j is the objective function which we want to optimize. Um Theta is the parameter. So if we looked at linear separator, theta were the parameters of the linear separator, like theta 1 x1 plus theta 2 x2 plus theta not equal to 0. If we look at this, then the parameters are theta 1, theta 2, and theta naught. And j is the objective function. So the optimization problem essentially is this. The optimization problem is to find theta star that minimizes j. So think of the positive and negative points which we had and we found the linear classifier. The objective in optimization is to find the theta 1, theta 2 and theta naught, so that in that particular example the loss which it makes on predictions is reduced. This is the simple definition of the optimization problem. Now you may be thinking, what is this objective function, and what does it look like for machine learning problems? So in any machine learning problem, the objective function typically looks like this. First, I'm going to write it in words, and then I'm going to write it in mathematical formula. So the objective function j of theta is always the summation of the loss on training data. So we want to minimize the loss on training data, plus there is an additional term which is called as regularizer. We will learn more about this just in a moment. But regularizer actually helps us to minimize or reduce loss on test data. So as we saw, it is not enough to just make sure that the loss on training data is minimized. We need to make sure that when any new data point is given, the machine learning algorithm which we had makes very less mistakes on new data points as well. So we need to minimize loss on test data as well. And for that, a technique called regularization is used. So let us see what this summation looks like mathematically. Mathematically, this just looks like 1 by n, which is the number of data points. Sigma I goes from 1 to n. L, which is my loss function. H, this is my hypothesis. So basically, this is the loss function. Um, this is the loss function averaged for all the n points. So I'm dividing it by n. Then this h is our guess, and this y is the actual value. Basically this just means that you take your hypothesis, you make the guess, and then you find the error between the guess and the actual value. That's the loss function, and we just take the average of the loss function over all the training data. uh, and the regularizer looks like this: lambda into r of theta. So this lambda is the hyperparameter. And remember, we saw this in the random linear classifier algorithm, where lambda we randomly chose to be equal to, let's say, 100 variations or 100 iterations. So lambda is the hyperparameter, and this is called as the regularization function. So, or we can just call it regularizer here. You can think of the regularizer as putting a penalty on our thetas. So it says that the reason we put a penalty here is that we are telling the algorithm is, don't try to perfectly or to super accurately fit the data. Don't try super hard to fit the data, because that might lead to an overfitting problem. Try to keep the algorithm, or try to keep the optimal solution simple. Don't try to overfit. That is what we are telling in this regularizer. This is brilliantly summed up in this MIT's visual. So if you look at this particular data, let's say the black dots are the positive data and the hollow dots are the negative data. Let us compare two hypotheses, H1 and H2 here. Look at H1. H1 perfectly goes through all the points and it separates the positive, the black points from the hollow points, right? So we think that H1 is amazing. It makes no mistakes on the training data. But look at H2. H2 also kind of does good, but H2 makes one mistake over here. See, this black data it will classify as a negative data, uh, but it makes one mistake. So we might think that H1 is better than H2, right? But actually, if you think of it, H1 is better than H2 on training data. But if you look at testing data, we might prefer the solution to be simpler. So we might prefer H2 over H1, because H1 actually is trying to go through the training data points one by one. So it is very specific to the data set which is there, right? So if a new data is given, H1 might make more errors than H2. Whereas H2 is a simple prediction, and it will perform better on future examples which are drawn from the same distribution. So H2 might perform well on the test data compared to training data. So another nice way of thinking about regularization is that we would like to prevent our hypothesis on becoming too dependent on the particular training data. So H1 is too dependent on the particular training data. So it makes mistake on the test data. So regularization helps us to prevent our hypothesis from being too dependent on the training data that we were given. We would like for it to be the case that if training data were changed, our hypothesis does not change that much. This is very important. But now if this point is removed, if this black point is removed, H1 will suddenly change completely, but H2 will remain the same. So H2 is more robust for testing. And regularization, so uh, if the objective function did not have the regularization, uh, we would optimize for a solution which looks like H1. That would be our solution, which is not a good solution on testing data. But if we have this regularizer, we might discover simpler solutions like H2, which do not overfit and which might perform better on the testing data. So this is our objective function. So one way of finding an ML algorithm now, the way to find ML algorithms are to find the hypothesis H which minimizes the objective function, minimizes J. That's it. And this is an optimization problem because there are so many thetas, right? There are so many thetas which can lead to different values of J. We need to find that particular theta which leads to the lowest possible value of J. And that will be our final answer. So we have effectively boiled this down to an optimization problem. That's the first intuition I wanted to provide you, that all the things which you see right now, gradient descent, Adam optimizer, all these optimizers, the reason why optimization is so important in machine learning is that all modern ML techniques are formulated as optimization problems, where we have to optimize for the weights in a neural network or the parameters in gradient descent, etc. There are very few algorithms like perceptron, which is not an optimization problem, but it starts from human intuition. Now that we have this idea, let us look at part 2 of this particular lecture, which is logistic regression. Another name for logistic regression, which is used in MIT's lectures, is linear logistic classifiers. But in literature, in all ML textbooks, the most commonly used terminology is logistic regression, so we will stick with it. We will need one more or two more lectures to cover everything related to logistic regression, but today will be a good start. So essentially, logistic regression, the problem is the same. We have negative points, which is one type of data, and we have, or rather, positive points, which is one type, and negative points, which is another type. And we need to find the linear hypothesis which separates the two. That is still the problem, but now we are looking at a new technique of solving this problem. So let us look at optimization. So if we want to formulate this as an optimization problem, we need a hypothesis H and we need a loss function L. We will look at the regularization term later, But if we want to formulate this as an optimization problem, we will need L, which is the loss function, and H, which is the regularizer. Let us recall what we used for the loss function in perceptron. So recall, in perceptron we use the 0 1 loss. We use the 0 1 loss, where we said that, let's say we have our guess and the actual value. We said that the loss is equal to 1 if the guess is not equal to the actual value, and the loss is equal to 0 otherwise. This is also called as the 0 1 loss, by the way. 0 1 loss. So this says that as you're finding the best linear classifier, if the classifier makes mistakes on data, you say that the loss is 1. Whereas if it does not make mistakes on the data, you say that it's 0. So if you remember, we actually had the sine function, which is sine of theta transpose x plus theta naught. So if so that this was our hypothesis. This was our hypothesis H, and this was our loss function L for the perceptron, which is called a 0 1 loss. Now your question would be that, okay, let us use this uh, this loss function and this hypothesis, the sine function, and then let me try to optimize this. So can I find, you might think that, can I find theta and theta naught by optimizing the 0 1 loss? You see how this is different than the perceptron. In perceptron, we did not find any, we did not do any optimization, right? Still, the perceptron converged to the correct answer. But uh, the question is, can I find theta and theta naught by optimizing this loss function, which is the 0 1 loss? Now, perceptron does a good job of optimizing this loss function if the data is linearly separable. But if the data is not linearly separable, we cannot rely on perceptron. So we have to perform this optimization procedure. Now it turns out that if you look at the 0 1 loss and if you plot the 0 1 loss, it actually looks something like this. Um, if the input to the loss function is negative, the answer will be -1, or as we have seen here, it will be 1 or it will be 0, right? So let's say my x-axis is theta transpose x plus theta naught, and my y function is the 0 1 loss. So if theta transpose x plus theta naught is greater than 0, uh, then my loss will be equal to 1, or otherwise my loss will be equal to 0. This is how the function actually looks like, or rather, yeah, this is how the actually hypothesis looks like. The 0 1, if theta transpose x plus theta naught is greater than 0, so this is the sine function. I'm sorry, on the y-axis we don't have the 0 1 loss, we actually have the sine function. And if theta transpose x plus theta naught greater than 0, then the sine function is +1. And if theta transpose x plus theta naught is less than 0, the sine function is -1. Now it turns out that if we just use this loss function, the 0 1 loss, and if we use this hypothesis class, then it is very difficult to solve this optimization problem mathematically. So mathematically, it is impossible rather to minimize the 0 1 loss. And there are many reasons for it, because this function is non-differentiable. uh, it suddenly jumps here at 0. It is not really smooth. So mathematically it's also called as an NP. So if you are not familiar with this, it's fine, but it's an NP hard problem, which means that it's impossible to optimize the theta if we have this particular hypothesis class and the loss function which is a 0 1 loss function. So this needs to change, right? And that is where the idea of the sigmoid function comes in. So what do we do? What do we do? We started out with this idea of formulating the ML as an optimization problem, but we saw that this particular hypothesis class, if we use the sine function as the hypothesis class, the loss function cannot be optimized. So this is where the sigmoid hypothesis class comes into the picture. This is where the sigmoid hypothesis class comes into the picture. And the main idea of the sigmoid hypothesis class is that what if uh, the loss function was not like this? So, or what if the hypothesis class was not like this? So, if this is theta transpose x plus theta naught, the current hypothesis class which we have, which is the sine function, is like a ramp function. So if the theta transpose x plus theta naught is negative, it will be 0 or else it will be 1. So there is this discontinuity here. So then the what people thought was, what if we make this smooth? So what if it was something like this? What if it was a smooth function without any discontinuity? What if this can be our new hypothesis class instead of the sine function? Then hopefully we might be able to optimize it, right? Then we might be able to optimize the loss function. So hopefully the smoothness of this data, the hopefully the smoothness of the hypothesis class will help us optimize the loss function. So which might make it mathematically possible. And it actually turns out that it does make it mathematically possible to evaluate the loss function in this case and to even optimize for the loss function. So now let us look at it mathematically to see what the sigmoid function actually looks like mathematically. We know that it looks something like this visually, but mathematically the sigmoid function looks like this. So sigmoid, it's also denoted by sigma, and sigma of z is 1 divided by 1 plus e raised to minus z. And if you plot this particular function, it looks like this. For x equal to 0 or for z equal to 0, if you put z equal to 0 here, e raised to 0 is 1. So it will be 1 divided by 2, and so the answer will be zero point 0.5. For very high values of z, for let's say z equal to infinity, this will tend to 0. So this positive side will tend to plus 1. So the positive side of the graph looks something like this, where this is plus 1, and the negative side of the graph tends to look something like this. This is equal to 0. So as z is becomes more and more negative, e raised to minus z will tend towards infinity. So then 1 divided by infinity will tend to 0. So as we go further in this direction, this will approach 0, and as we go further in this direction, this function will approach 1. Note that it never becomes 0 or it never becomes 1, and it always lies between 0 and 1. Now let us actually compare the sigmoid function and the sine function. So the sine function, as we saw, looks like this, right? Sine function, as we saw, looks like something like this ramp. So this is the sine function. There are two distinct advantages of the sigmoid function over the sine function. The first advantage of the sigmoid function is that it is continuous. It is continuous and it is differentiable. So just it has good mathematical properties. It is continuous and differentiable. So it helps us solve the optimization problem. That's one major advantage. And the second advantage is that it offers actually more information. What I mean to say is that if this is theta transpose x plus theta naught, the x axis scale, let's say we take 2 points on the x axis, okay, this point and this point, right? The theta transpose x plus theta naught will be negative for both of these points, correct? So the value will be equal to 0 for both of these points. And we don't know whether our prediction is closer for one point or closer to another or closer for another point. We just know that the prediction makes a mistake for both of these points. But if you look at this particular plot, and if you look at a point which is far over here, let's say this is my point A and this is my point B, and let's say here we have point C and here we have point D. Now if you see the point C, its value will be somewhere equal to zero point 0.7, and point D, its value will be somewhere very closer to 1. So we know that the hypothesis value is positive for both these points, but we also know something more. We know that it is more positive for point D and it is more positive for point C, right? And so if the true classes of point C and D were positive, we would know that the prediction on D is more closer to the correct answer than C. Although both of them would give correct answer if the true value is positive, but we know that the prediction for D is better because it is more closer to plus 1. And it turns out this is actually a this information is really helps machine learning algorithms as they learn about the data. Whereas if you look at points A and B, and let's say their true prediction was negative, so we will know that both uh, A and B, uh, they they give negative values, correct? But the value of A is more negative than the value of B, and this might probably indicate that the prediction for A is much closer than the prediction to B, although both give the correct answer. So what I'm trying to say here is that the sigmoid function actually gives us one layer of better understanding than the sine function. So apart from good mathematical properties like being continuous and being differentiable, it also gives us more information about how our algorithm is potentially performing, and that might help the convergence of the ML algorithm when we move to that stage later. There is also an intuition. So the intuition for the sigmoid function is that so the intuition for the sigmoid is that if the sigmoid function is closer to 0, we are more sure or we are more probable that x is negative, because then we will lie somewhere here if the sigmoid function is closer to 0. If the sigmoid function is closer to 1, then we are more probable or we are more sure that x is positive, because then we will lie somewhere over here. Uh, but if the sigmoid function is closer to zero point 0.5, then we don't really know. Um, yeah, if the sigmoid function is closer to zero point 0.5, then we don't really know. And the reason we don't really know in this case is because if the sigmoid function is closer to zero point 0.5, which means our x value lies somewhere here. So we don't know whether it's positive or we don't. So we don't know whether it's negative or we don't know whether it's positive. So the intuition for sigmoid is that it's also kind of related to the probability of our input being positive or our input being negative. And this kind of intuition is really exploited by machine learning algorithms. So now let us see how to actually make sigmoid into a classifier. So if you see how to make sigmoid into a classifier. So it's pretty simple actually. You can just look at this plot, and if let's say the sigmoid value is greater than zero point 0.5, uh, it means that the input is positive, right? Like theta transpose x plus theta naught is positive. Whereas if it's less than zero point 0.5, if the sigmoid value is less than zero point 0.5, it means theta transpose x plus theta naught is less than 0, correct? So basically, the to make a classifier, what we are going to do is that our hypothesis will now be, if our hypothesis h of theta will be uh, plus 1 if sigma of theta transpose x plus theta naught is greater than zero point 0.5, and our hypothesis will be equal to minus 1 if sigma of theta transpose x plus theta naught is less than zero point 0.5. That's it. So this is our new hypothesis class. You can see how it is different from the previous thing, right? The previous we had the sine function here instead of the sigmoid function. So the only difference is that we have replaced the sine function with a sigmoid function. Yeah, so the only difference is that we have replaced the sine function with the sigmoid function, which is continuous and which is smooth. And why we are doing this? We are doing this for two reasons. The first reason, it makes the optimization easier. It makes optimization easy. That's the first reason. And the second reason, as I mentioned, it gives us more information about whether we are correct for a particular point or not. Rather than just saying positive or negative, it gives us answers on a continuous scale, which is useful for our ML algorithm later. Now I want to move to part number 3 of this particular lecture, which is visualizing visualizing the sigmoid hypothesis. So we will visualize it for 1D and we will also visualize it for 2D. Note that we are not looking at the loss function in this particular case. Up till now, we have only discussed about, if you look at the algorithm, up till now, we have only discussed about the H, which is the sigmoid hypothesis class, uh, which is this particular hypothesis class. We have not yet discussed about the loss function, which we will do in the next lecture. But what I want to show right now is how to visualize this hypothesis in Python. How to visualize the sigmoid function in Python. The reason I want to show you this visually is that if you have a visual clarity, right, later it will always remember in in your mind, even if you forget the mathematical formula for sigmoid. Even if you forget this formula, it's fine. You should have the intuition in your mind. So I'm going to VS Code again. Again, I don't want to go through the code, but I'm using NumPy and Matplotlib for the plotting. I'll be sharing the code also. What I want to show you is these plots. So imagine that we are in one dimension right now. We have 2 points whose actual class is positive and 2 points whose actual class is negative. What I'm showing here is the sigma function for these 4 points. So the sigma, if you have just one dimension, right? then the sigma function will be just 1 upon 1 plus e raised to minus that particular x. That is all what I'm plotting here. So these blue lines are y equal to 1 upon 1 plus e raised to minus x, and x is the theta. So 1 upon 1 plus e raised to minus theta x plus theta naught. Um so this is in one dimension. So theta actually will just be one feature. So there won't even be a theta naught. So what I'm actually showing here is this function for different values of theta. Remember that what we are doing in this when we finally optimize is we want to find the best theta, right? But first I want to show you what the function itself looks like in one dimension. So if you look at the sigmoid function, these are different values of theta and theta naught. So theta naught for all cases is 0, and what I've varied in that plot is I've varied theta values for four different options, and let us evaluate those four. First of all, let us see this. If theta equal to minus 1, this is the hypothesis class, and it predicts a positive value for these 2 points, and it predicts a negative, or rather it predicts a value greater than zero point 0.5 for these 2 points, and it predicts a value less than zero point 0.5 for the blue points. Now see what it means. If it is less than zero point 0.5, it means it predicts a value of minus 1. So essentially it predicts a value of minus 1 for the blue points, which is wrong because the blue points true value is positive. So this theta is clearly not correct. All other thetas, if we look at, they have a similar orientation. So they all are correct because for all of them, if you see, values greater than zero point 0.5 are associated with blue points, and values less than zero point 0.5 are associated with red points, which means that our hypothesis will classify these blue points as positive and red points as negative, which is correct. But when I said this sigmoid also gives more information, now look at the more information. If I ask you the question, among these three plots, which of the plots is the best predictor, what will you say? I'll pause here for some time. So all these three make the correct prediction, right? But which of the following makes the best prediction? Okay, we have not defined the loss function yet, but I just want to give you the intuition. If you look at these two plots, you will see that the y values for the negative points are not that close to zero. They are kind of point two. They are kind of point. They are kind of around point one to point two. Whereas if you look at this plot, the y values for minus one and minus two are very close to zero, which means that in this plot we are more probable, or we are very much sure about these red points being negative than these plots. Similarly, if you look at the positive points and if you look at the y values, they are not close to 1. They are close to zero point 0.6 or they are close to zero point 0.8. Whereas if you see this plot, the y value is very much close to 1, which means in this plot we are very sure about predicting the values for the training data points. Again, you might say that this plot might be overfitting the data, but that is fine. We'll see that when we look at the loss function. But already you can see we have started to derive so many insights. If this was just a sine function, all these three plots will look the same. But right now it's not the sine function. It's like it has a continuous scale from 0 to 1. So then we can see which of these plots are more closer to 0 for negative points, and more closer to 0, more closer to 1 for positive points. Because remember, the sigmoid function also is related to probability, right? So this fourth plot actually is more probable. We are more probable that the blue points are positive because it's closer to 1, and we are more probable that the red points are negative because it's closer to 0. So I would actually prefer this fourth plot. That's the added advantage of the sigmoid function. So this is for 1D classification. Let us look at what the sigmoid hypothesis class looks like for 2D points. So similar to 4 points which I've taken here, two positive and two negative, I am going to take 4 points in the 2D space. Don't be confused or intimidated by this graph. Let me zoom in further. So the blue points are of the positive class, and the red points are the negative class. What I'm plotting here, the three-dimensional thing is y is equal to 1 upon 1 plus, or rather z is equal to 1 upon 1 plus e raised to minus theta 1 x1 plus theta 2 x2 plus theta naught. So if you plot this in three dimensions, it will actually look like a plane, right? Now, again the same thing will happen. What we will do is we will evaluate whether z is greater than zero point 0.5 or less than zero point 0.5. So if you look at this, I have just shown one particular in this plot. I have just shown, for the sake of clarity, I have shown the perfect separator, which means I have chosen the theta 1 to be theta 1 star, theta 2 star, and theta naught star. So if you look at the positive points, if you look at the blue points, you will see that the z value, which means that if you extrapolate it onto this plane, you will see that the z value is greater than zero point 0.5, correct? Which means that our hypothesis class will also predict them to be positive, which is good. If you look at the three red points and if you project them onto the plane, they all lie somewhere close to zero. So the z value is less than zero point 0.5, which means that our hypothesis class will predict them to be negative. So this looks like the best hypothesis. And I've also projected it on the XY plane to see how the separator actually looks like in 2D. So this green line is the 2D separator. I am right now showing you the optimized plot, but remember we have not yet arrived at this. Up till now, we have only arrived at looking at the hypothesis. Up till now, we have only constructed the hypothesis. The next step would be to define a loss function. The next step would be to define a loss function, and the step after that would be to optimize the theta so that the loss function is minimized. And only after these two steps are completed, we will get an optimized solution like this separator. Until these two steps are completed, the hypothesis class can be this or this or this or this. We don't really know. We will optimize it only when the loss function is minimized. Then we might get an optimizer or the final hypothesis class which looks something like this for the best value of theta and theta naught. Okay, so this actually brings us to the end of this particular lecture. It was a pretty intensive lecture where we looked at uh, three things. We looked at solving machine learning problems using optimization methods. Then we also saw about logistic regression, and then we learnt about the sigmoid function. We also learnt about the hypothesis class for the sigmoid function in this lecture. In the next lecture, we will learn about the loss function, and we will learn about optimizing the loss function. In the meanwhile, we also saw that if we just have a 0 1 loss, right, and the corresponding sign hypothesis, it becomes very difficult mathematically to solve this optimization problem. And that's the reason people came up with the idea for a sigmoid function, so that we can smooth out the hypothesis instead of having this big jump from 0 to 1. And that smoothing out leads to wonders because it solves two things for us. It makes the function hypothesis continuous and differentiable, which helps us in the optimization problem, and it also leads to more information. So for example, we can now compare between these four plots, and we can choose which hypothesis is better than others, especially these three. Although all these three plots classify the points correctly, looking at how close the negative points are to 0 and how close the positive point prediction is to 1, we can classify, or we can assign some differences to the sigmoid function. We also saw an intuition for the sigmoid that it is kind of related to the probability. If the sigmoid function is closer to 0, it is more probable that x is negative. So in this plot, the sigmoid function is closer to 0. So we are more probable in this plot that these red points are negative than in these other two plots. Similarly, if it's closer to 1, we are more probable that x is positive. So here if you see, This plot, the blue points are also more closer to 1 than these two. So we know that with more probability that these points will have a positive prediction. Finally, if it's closer to zero point 0.5, we don't really know, since it can be either negative or positive. In the next lecture, we are going to be looking at defining the logistic regression loss function, and then we will also construct or mathematically see how to optimize for the theta. So you'll learn about the logistic loss regression, and we will also then implement it in Python. The Microsoft course, if you look at it, it does not have any of these details at all. It just has the Python example for logistic regression, which we also will come to. Uh, but in this course, I also wanted to provide you with all these foundational material, so that when you implement these things in Python, you know intuitively what the sigmoid function is. You intuitively know what it means to formulate an ML problem as an optimization problem, etc. But if you directly start with the Python, all this intuition will be lost. My notes have been uploaded in the YouTube video information, so those will be useful for you. Thank you, everyone, and I'll see you in the next lecture.